What if a single roadside plant, the kind you might walk past without a second glance, could become a living factory for fertility, a perennial source of nutrients that, in the right hands, dramatically cuts the need for bagged fertilizer? And what if, just as that possibility was becoming visible again to gardeners and small farmers, a regulatory advisory sent its retail presence into retreat? Today, I'm following a trail that runs from ancient herbalists to Victorian breeders, through mid-century trials and a controversial advisory in 2001, to the backyards and market gardens where people quietly use the plant known as comfrey, and more specifically, a cultivar called Bocking 14, to build soil and feed plants. Spoiler, it's powerful, it's complicated, and it's not the same thing as the FDA banning a garden plant. But it does suggest a different future for how we grow fertility. Centuries ago, herbalists from Dioscorides to Pliny made note of comfrey's tough reputation, a plant with thick, fuzzy leaves and a willingness to grow in marginal ground. They were talking primarily about medicinal uses, wounds and poultices, and a belief in its ability to knit things together. Fast forward to the mid-1800s, and you meet a different kind of evangelist, Henry Doubleday, an English breeder who watched the human cost of failed harvests during and after the potato famines and turned his attention to plants that could help people feed themselves. He and others experimented with crosses and collected observations about astonishing biomass and regrowth. Some of those stories slip into the realm of legend. Reports like 100 tons per acre exist in the record as extraordinary claims, often linked to 19th century anecdotes and rare trials. They're worth repeating because they shaped how people thought about the plant, but they need asterisks. They were reported by specific growers under particular conditions, not guaranteed yields for every field everywhere. In the 20th century, a horticulturalist named Lawrence Hills took this older lore seriously. He worked to identify and preserve the most useful comfreys, and out of that effort came Bocking 14, a sterile, clonally propagated hybrid that combined the traits people wanted most: vigorous, high biomass growth and the ability to be shared freely through root cuttings. Hills and the organization he helped found distributed Bocking 14 widely and explicitly with the idea of decentralizing fertility. Grow a clump once, share cuttings, and your patch of garden can be fed year after year without recurring purchases. That free distribution is an important thread in the story. It wasn't promoted as a commercial product to be bought and sold by the ton. It was promoted as a tool for gardeners and smallholders to be passed between hands. So what makes this plant so interesting from a scientific point of view? Three things working together. First, the roots.
Comfrey develops a deep, thick root system that acts like a biological mining drill. In many soils, it will send roots well beyond the topsoil into subsoil layers other crops rarely touch. Those deep roots access minerals, potassium, calcium, phosphorus, and micronutrients that have leached below the reach of shallow-rooted plants. Over the season, the plant translocates a portion of those minerals into its leaves and stems. In effect, comfrey can lift nutrients from depth into readily available biomass at the soil surface. Second, the leaves. Multiple laboratory analyses of comfrey leaf tissue show unusually high concentrations of certain nutrients compared to typical farmyard manures or green manures. For example, some measured samples registered potassium levels in the ballpark of what would be considered high for a green biomass crop. Studies and nutrient analyses sometimes cite figures around several percent K on a dry weight basis. A few samples have been reported near or around 7% K in dried tissue. That makes the plant especially valuable where potassium is the limiting nutrient. Calcium and phosphorus are also present at meaningful levels, and the sheer mass of leaf material produced per cut means a single harvest can move a significant nutrient payload into your garden. Third, decomposition behavior. Comfrey leaves break down very fast under active microbial conditions. In hot, aerobic compost piles or on warm soil, freshly chopped comfrey can lose its structure and begin to integrate into the compost mass in a matter of days rather than weeks. Gardeners commonly report that a comfrey mulch quickly settles and becomes soil-like, and experimental composting trials have documented rapid decomposition under optimal conditions. That rapid decomposition translates into nutrients becoming available to plants more quickly than some other green manures. Put those three effects together: deep mineral mining, nutrient-dense tissue, and fast breakdown, and you have a plant that acts like a living pump. Pull minerals from deep down, concentrate them in leafy biomass, and return them to the root zone where other crops can use them. For small-scale, intensive, and perennial systems, that's a profound tool. It's why some permaculture practitioners call comfrey the nutrient accumulator or biological nutrient pump. But here is where history and policy complicate the story. The 20th century brought an industrial solution to the soil fertility problem, the Haber-Bosch process. It allowed nitrogen to be synthesized from atmospheric air on an industrial scale using fossil fuel energy, and it underpins the synthetic fertilizer industry that feeds a large portion of the world's crops today. The convenience was transformative: predictable nutrient supply, enormous scale, and high yields. It also created a recurring purchase model.
Synthetic fertilizers are an industry measured in hundreds of billions of dollars annually. They're tied to global natural gas markets and concentrated supply chains. A low-cost perennial that, for many growers, reduces the need to buy fertilizer year after year, challenges that model by decentralizing where fertility comes from. That tension between centralized, fungible nutrient supply and decentralized, living fertility plays into how Comfrey has been treated in public discourse. In 2001, the U.S. Food and Drug Administration issued an advisory concerning Comfrey in internal dietary supplements, citing the presence of pyrrolizidine alkaloids, or PAs. PAs are naturally occurring compounds found in several plant families. In Comfrey, certain PAs have been associated with liver toxicity in documented cases of prolonged ingestion. The FDA's action targeted internal uses, pills, tinctures, and other ingestible products, and urged removal of Comfrey-containing internal supplements from the market because of the documented risk of hepatic veno-occlusive disease and related concerns. Two important clarifications flow from that regulatory moment, because the headlines that followed often muffled these nuances. First, the advisory was about ingestion, internal consumption of Comfrey products. It was not an order to stop growing Comfrey in gardens or to stop using it as a mulch or compost source. Second, the public reaction and consequent commercial choices had wider effects than the letter of the advisory. Many nurseries delisted Comfrey or stopped carrying certain varieties rather than navigate customer confusion and liability risk. At the same time, small gardeners steeped in permaculture practice quietly continued to grow, share, and use Bocking 14 as a fertility tool, mostly for external applications. So while the FDA did not outlaw Comfrey beds, the advisory had the practical effect of reducing mainstream retail visibility and amplifying public misunderstanding. That brings us to a crucial safety point: the difference between external and internal use. When we talk about mulching with comfrey leaves, mixing chopped comfrey into compost, or using a diluted comfrey tea as a foliar or soil feed, that is external horticultural use. The main safety concern that led to the FDA advisory, chronic exposure to pyrrolizidine alkaloids through ingestion, is not the same as spreading comfrey mulch on a vegetable row. However, it's also not accurate to say there is zero risk in every external practice. PAs are plant compounds. Some studies suggest microbial composting and soil processes reduce their concentrations over time, and high-heat active composting seems particularly effective at breaking them down. But the speed and completeness of that breakdown depend on conditions: temperature, aeration, microbial activity, C to N balance, and the starting material's particle size.
In other words, rapid composting under proper conditions will reduce PA levels more reliably than leaving whole leaves piled and slowly rotting in cool anaerobic piles. Because research is incomplete, the cautious recommendation is sensible. Avoid making comfrey-based preparations intended for internal use. If you're using comfrey as mulch or compost, aim for hot, active composting or well-integrated mulch, so microbial processes have every chance to break down PAs before crops are harvested for consumption. What does that look like in practice for gardeners who want to experiment responsibly? First, source and planting. Bocking 14 is sterile and spreads by root division, which is why garden communities have maintained it by trading root cuttings for decades. If you can find root cuttings from a trusted source or a fellow gardener, plant them in a spot with room to grow. Comfrey thrives in full sun to partial shade and prefers reasonably fertile, well-drained soil, but is forgiving of poorer soils because of its deep roots. Plant a clump and you have an investment that will produce for many years. Harvesting is straightforward. Many gardeners make their first cut once plants are well established and about 2 feet tall. You can cut back to near ground level. Comfrey regrows rapidly, often in as little as 4 weeks in warm, favorable conditions. In temperate climates with long growing seasons, 5 cuts in a season is not unheard of. Fewer cuts are normal in cooler regions. The key is to harvest before flowering if you're managing for biomass rather than seed production. Bocking 14 is sterile and rarely sets viable seed, which is part of what makes it manageable. Use the green biomass as fresh mulch around fruit trees, brassicas, and heavy-feeding crops. Lay it on the soil surface and allow microbial activity to begin integration. For composting, chop the material to increase surface area, mix with higher carbon dry materials like straw or shredded leaves to balance the pile, and build a hot aerobic compost if your goal is rapid breakdown. Under active composting, comfrey tissue loses structure quickly and contributes to a rich, dark humus faster than many alternatives. If you prefer liquid fertilizer, you can make an external comfrey tea by steeping chopped fresh leaves in water for a period and using the strained liquid as a diluted soil drench or foliar spray. In all external uses, label and treat the product as a garden fertilizer fertilizer, not a food or medicine. A few technical points to keep expectations realistic. The extraordinary historical figures, like the oft-cited 100 tons per acre, are part of the lore and do appear in older accounts and some growers' records. Those accounts are remarkable and should spark curiosity, but they represent specific instances, often under ideal conditions and with selective reporting.
Modern agricultural trials from Britain and elsewhere in the 20th century reported very high biomass yields and meaningful nutrient returns, but results vary by soil, climate, cultivar, and management. Likewise, nutrient analyses show Comfrey is unusually rich in certain elements compared to many green manures. Samples showing very high potassium levels have been documented, but not every patch of Comfrey will measure the same. Scientific humility matters. Treat these numbers as indicators of potential rather than guarantees. Now to the elephant in the room. Could Comfrey replace all fertilizers forever, as the clickbait version of this title suggests? My measured answer is no. Not overnight, not across every cropping system on the planet, and not without careful local adaptation. Large-scale commodity agriculture, especially industrial monocultures planted by the thousands of acres and dependent on precise high-ratio nutrient applications, operates under constraints and economies that a garden clump of Comfrey cannot instantly match. But that misses the real point. For millions of smallholders, market gardeners, peri-urban growers, and backyard gardeners, a network of Comfrey clumps, each one a living store of nutrients, could substantially reduce reliance on purchased fertilizers. That's decentralization. It doesn't erase the need for synthetic inputs in all contexts, but it reshapes the balance where labor, land access, and multi-cropping systems make perennial nutrient pumps practical. There are also systemic implications. If more communities invested in perennial fertility systems, Comfrey, dynamic accumulators, agroforestry, the aggregate demand for some synthetic fertilizers could drop. That would alter markets, supply chains, and perhaps even the political economy of fertilizer production over decades. It won't happen because of a single plant alone. It would require knowledge sharing, local experiments, and supportive policies that recognize soil building as a long-term investment rather than a quarterly sale. So what now? If this story intrigues you, there are sensible next steps that won't put you or your family at risk. Grow a clump from mulch and compost, share root cuttings with neighbors, and experiment with Comfrey tea on non-edible ornamentals first if you're cautious. When using Comfrey and compost, favor hot, well-managed piles to accelerate microbial breakdown and reduce any residual pyrrolidine alkaloid content. Don't make tinctures or internal remedies from Comfrey. The safety data for ingestion are the reason regulators acted in 2001. And when you read dramatic yield figures, treat them like leads to be investigated rather than promises. I've been following archival references, Lawrence Hill's writings about Bocking 14, a handful of mid-century British trials, and modern nutrient analyses, and I'll put the sources I used in the video description so you can read the primary material for yourself.
If this surprises you, that something so ordinary in appearance might be so significant in function, subscribe to follow the series, where we'll dig into specific trials, compare Comfrey to other green manures, and show step-by-step how to establish and manage a patch safely. In the end, Comfrey isn't a miracle cure for industrial agriculture's systemic problems. It is, however, a remarkably efficient biological tool for many growers. It's a reminder that some of the world's most useful technologies are living and shareable, rather than patented and packaged. If you want the sources, a careful how-to guide, and a place to download safe cultivation notes and cited studies, check the link in the description. Share this with a gardener or a neighbor who keeps asking, is there a better way to feed soil? Plant a clump, pass a cutting, and join the quiet work of building fertility. Because small, repeated acts at the local level add up into systemic change.